Hello and welcome to this explainer. Today we're going to totally master linear relationships. And we're going to do it in a way that goes way beyond just staring at abstract letters and numbers on a page. Actually, we're going to put these concepts straight to work by planning a massive end-of-year school event. Whether you're building a budget, analyzing some data, or just trying to compare costs to get a good deal, linear relationships are literally the fundamental mathematical tools that help us make sense of the real world. Okay, let's quickly run through our agenda for today. We'll kick things off with planning the school event, then move into slope, intercepts, and units. After that, we'll hit systems and intersecting lines, followed by budgets and constraint regions, and then we'll wrap it all up with a quick recap and a transfer task. All right, section 1, planning the school event and setting the stage. Let's jump right in. So I want you to imagine you're the one in charge of planning the big end-of-year school dance. It's a huge responsibility, right? And your very first major hurdle is figuring out the financials. You have to compare different catering and venue options to make sure the event is incredible, but without completely draining the school's funds. To do this, we're looking at two competing proposals. First up is Plan A, which has a higher fixed cost just to rent the venue, but they offer a much cheaper rate for the food per student. On the flip side, we have Plan B. They offer a lower fixed venue cost upfront, but their catering, yeah, it's pricier for every single student that walks through the door. Having these two verbal descriptions of our event costs perfectly sets up our mathematical conflict. We need to know which one is actually the better deal. If we organize Plan A into a table, things start to become a bit clearer. Mathematically speaking, the number of students is our input, or the independent variable, and the total cost is our output, our dependent variable. Notice how for 0 students, the cost sits at exactly $100. That's just our fixed venue fee. Then for every single student we add, the cost goes up by exactly $10. What we're seeing here is an arithmetic sequence. We are adding the exact same constant amount per student, which establishes a perfectly clear linear function where each specific input maps to exactly one output. Moving right along to section 2, slope, intercepts, and units, or what I like to call the language of lines. Transitioning from a simple table to an actual algebraic equation means we really need to understand this language. And the absolute most crucial thing to remember here is that our intercept and our slope, they aren't just random abstract letters in an equation. They represent exact real-world units. The y-intercept is our starting value and the input is 0. So for our event, this is the fixed venue cost, strictly measured in dollars. The slope, on the other hand, is our constant rate of change. It tells us exactly how the output shifts for every single unit increase in our input. So for Plan A, this rate is measured in dollars per student. Okay, before we even think about graphing anything, it's time for our first pause check. I want you to just pause for a second and think. Mathematically, the domain is the set of all possible input values, right? So for our specific school event function, what is the actual real-life domain for the number of students attending? Well, if you guessed whole positive numbers and 0, you nailed it. Because the specific context of our function dictates a restricted domain, we can't just plug in any random number we want. I mean, you literally cannot have half a student show up to the dance, and you for sure can't have -3 students attend. The real world dictates our mathematical boundaries here. Now, this brings us to a major misconception that a lot of people have. So many folks think any straight line on a graph is just this interchangeable, generic geometric shape. But in reality, a line isn't just a line. Without paying close attention to a specific scale, precise units, and a restricted domain, like our whole number rule for students, a graph is completely meaningful for actually analyzing our event. Context is what gives the math its real power. All right, section 3 already, systems and intersecting lines. Let's find that balance. To actually figure out which plan will save our schools some money, we can translate both of these plans into linear equations. Plan A has a $10 rate of change and a $100 initial value, so that gives us y equals 10x plus 100. Plan B has a $15 rate of change and a $50 initial value, which gives us y equals 15x plus 50. When we write both plans out as linear equations and look at them side by side, we've just created what's called a system of equations. And this brilliantly illustrates our break-even point. If we were to graph these two lines, the solution to the system is the single exact point on the graph where the two lines cross. At this intersection, the input, the number of students, yields the exact same output, the total cost, for both plans.
Once we locate this single point, we know exactly when Plan B stops being the cheaper option and Plan A takes the lead.
But hey, what if we threw a Plan C into the mix? Let's say it charged the exact same $10 per student as Plan A, but it had a steeper venue fee of $200. Because they share the exact same rate of change, their lines would be perfectly parallel, meaning those two pricing models would never ever intersect. Plan C would always just sit there being more expensive. And just as a quick geometric side note while we're talking about lines, if a line were to cross ours at a perfect 90-degree angle, it would be a perpendicular line, which completely requires an opposite negative reciprocal slope.
Moving on to Section 4, Budgets and Constraint Regions. It's time to face reality.
So we've modeled our costs beautifully, but let's be real, we aren't made of money. Which brings us to our second pause check. If our total school budget for this dance is strictly capped at $500, how do we show this mathematically? Pause for a second and consider how we would translate a maximum spending limit into algebra. Well, the answer is that we can no longer use a strict equation. We have to use a linear inequality. For example, our total cost y must be less than or equal to 500. Just this single shift totally changes our focus from one exact line of cost to a whole range of affordable possibilities. When you graph this, the budget inequality doesn't just draw a line, it actually shades in an entire area known as a half-plane. This half-plane represents the graphical solution to our inequality. It visually captures every single combination of student count and total cost that stays safely under that $500 limit and, won't bankrupt the school. But wait, the venue just called us back and they threw a second rule at us. They require at least 50 students to even book the room in the first place. So now our input x must be greater than or equal to 50. By adding this rule, we've essentially created a system of inequalities that we have to satisfy at the exact same time. We have a maximum budget to respect and a minimum headcount to meet. Because of this new rule, our final solution is no longer a single point, and it's no longer just a simple half-plane. It is the overlap region, which is also known as the constraint region. This is the exact shaded area on a graph where our budget inequality and our minimum attendance inequality successfully cross over. Any point sitting inside this specific overlap region satisfies all of our real-world conditions simultaneously. It's like finding the mathematical sweet spot. Finally, Section 5, let's do our recap and our transfer task. We have successfully built an entire event completely from scratch using algebra. So let's lock in what we've learned today with 3 key takeaways. Linear functions map inputs to outputs using a constant rate of change and an initial value. Systems of equations reveal a single point where 2 linear models are completely equal. And inequalities define half-planes and overlap regions to map out real-world constraints. Now, I'm going to leave you with this final transfer task to solve on your own. Imagine you were analyzing a school fundraiser's profit lines. What does the intersection point of total revenue and total expenses actually represent? And taking it a step further, what does the sheeted inequality region perfectly above that expenses line mean for your overall success? Really think about it. Solving puzzles like this proves that these linear relationships truly are the key to understanding the math all around us. Thanks for joining me on this explainer, and keep exploring.